In the previous lecture, we looked at the game of life, which was a particular cellular automata model, and in it we saw how we could get just amazing phenomena, right? How simple rules could aggregate to produce really sort of complex, novel outcomes. What we want to do in this lecture is look at an even simpler class of cellular automata models, and actually these are the original cellular automata models, and to try and figure out what has to be true about the model in order for it to produce different types of outcomes. Because remember, one of our core questions was, what kind of outcomes is the system going to produce? Is it going to go to equilibrium? Is it going to produce patterns? Is it going to be complex? Is it going to be chaotic? And what we want to do is we want to try and understand which of those things is going to happen. Now, we're not going to get a definitive answer, but again, by using a toy model, we're going to get some understanding of what leads to complex outcomes. All right, so first some history. Cellular automata were developed by a guy named John von Neumann, who is just a brilliant man. Von Neumann built one of the first computers known as the Johnniac or the ENIAC. He also was one of the founders of game theory and of growth theory in economics. So just a brilliant, brilliant mathematical mind. One of the things he came up with, and this was working with a guy named Stanislav Ulam, who's a mathematician, was really the simplest model he could think of computation, which is what's going to be called a cellular automata model. Now, his vision, these cellular automata, have been sort of studied in gory detail, including a recent book by a guy named Stephen Wolfram, who's the developer of Mathematica, called The New Kind of Science. And in this book, Wolfram explores to unbelievable depth, this is a 1,000-page book with hundreds and hundreds of illustrations, how the cellular automata model works. And Wolfram refers to this as a new kind of science because he's arguing for a computational, inductive way of looking at the world. Okay, so what are these models? What are cellular automata models? Well, again, they're exactly what we looked at the game of life, except for here, instead of being on a two-dimensional grid, things are on a one-dimensional line. So you can imagine as before, we've got a bunch of cells, and they can either be off, which would be clear, or they can be on, right? And so what we can do is we can just then sort of say, okay, how do these things evolve over time? Now, the difference between this and what we did before is that now if I have a cell here, right, sitting in the center, we're going to assume that it has only two neighbors. So before, in the grid world, each cell had 8 neighbors. Now it's only got 2. Now, the advantage of doing things with only 2 neighbors is, well, it's simpler, for one thing. And it also means we can exhaustively study, and that's why Wolfram's book is so thick, we can study every single one of these rules. So we can write down every single rule and then ask, how do the different rules work? What behaviors do they produce? And that sort of stuff. The other big advantage is it's going to be much easier to display these worlds than the other worlds because we can let time move along this axis. So what I can do is I can have this, here's the cell at this moment in time, maybe it's filled in, and then I can say what happens to it the next period, maybe it's off, and then I can say what happens to it the next period, maybe it's on. So I can represent time as sort of moving vertically down the page, right? So that's the models. Now I've got to decide, okay, what can the rules look like? Well, here's an example. So let's think about what a rule would have to look like. So if I think of this cell X, right here, this is the cell X. Now, it's got 2 neighbors, right? So neighbor 1, neighbor 2, or we could call these left and right if we want. We can ask, what are the possible states those things can be in? Well, it's possible that all of them could be off, and it's possible all of them could be on, right? Or it's possible only the one to the right is on, or only the cell itself is on, right? So we can think through, and there's basically 8 different possibilities. So what would a rule be? A rule just says, what do I do in each one of those states? So it could say, well, if I'm in the state where we're all currently off, then I'm going to stay off. And if we're in the state where we're all currently on, I'm going to go on. And it could say, well, if these 2 of us are on, I'm also going to go on. And then what you do is then you think about, okay, here's this cell. We start out with some initial configuration. We've got a whole bunch of cells, and some of them are colored in, and some of them are not. And then what they do is each cell says, well, what does my configuration look like? If I'm this cell right here, I notice that all 3 of my neighbors are on, so I go to the lookup table, see all 3 neighbors are on, and say, I'm going to be on next period. Okay? So all you do is for each cell, like so this cell right here, if I look at this cell right here, it's on, but its 2 neighbors are off. So I'd go up to the lookup table and say, okay, this is the configuration we're in right here, and it might say, in that situation, go off, so that means in the next period, it would stay off. So that's it. Time moves horizontally, and we have these rules that look, right? Now, one of the things that Wolfram does in his book is he says, okay, look, if you look across all these different rules, you can get all 4 of these classes of behaviors, right? So you can get, we talked about this before, you can get these fixed points, you can get alternation, you can get randomness, and you can get complexity. And so what we want to understand is why? Why do you get these things? What's true about the rules in order for this to be true? okay, in order to get these different types of outcomes. Okay. Now, before we go any further, okay, there's a lot of rules. How do we make sense of them? How do we keep track of what the rules are? Well, Wolfram has a really ingenious way of numbering these. So let's think about it. So if I'm in this state here, all off, well, there's two possibilities here, right? We could be off or we could be on. And if I think about this state, there's two possibilities as well. We could be off or we could be on. And that's true for every one of these. 2, 2, 2, 2, 2. So there's two different things I could put for each of these things. So that means that there's 2 to the 8th possibilities, which means there's 256 different rules. So now we think, holy cow, the whole universe of these rules is of size 256. There's 256 things we have to explore. That's why Wolfram's book runs to 1,000 pages, right? If you just give 4 pages to each rule, you suddenly, used up 1,000 pages. Now, Wolfram also comes up with an ingenious way of numbering these rules. What he does is he says, let's just give these the numbers 1, 2, 4, 8, 16, 32, 64, 128. And then what he says is, if it's on, right, then, so let's suppose that a rule, here, let me do this a different way. So suppose that if it's, this is our rule right here. These 3 are on. So then what he says is, we'll call this rule 2, 8, 128, and we'll just add up those numbers to give us 138. So that'll be rule 138. So what he does is he makes this first one with 1, the next one with 2, the next one with 4, the next one with 8, and so on. And this enables him to give every rule a unique number between 0 and 255. So the rule where everything's off is rule 0. The rule where everything's on, we just add up all these numbers and get 255. So this is going to give us a numbering system for the rules. Okay. So let's look now at some rules that create some interesting phenomena. This is rule number 30, right? Because we have 2 plus 4 plus 8 plus 16. And this rule says if all 3 of you are off, you stay off. If the one to the right is on or the one to the left is on, right, these two things, you go on. If you're currently on, you stay on. And then here's a little bit of an asymmetry. If the one to the right is on, you stay on, right? But if the one to your left is on over here, you go off. So let's think about what happened here. This one, and this one all have 3, all are in this state, right? We're all 3 off, so they're going to stay off. This one has one to the right on, so it's going to come to life, right? This one right here, this next one, is currently on with its 2 neighbors off, so it's going to stay on, right? This one right here has the one to the left on, so it looks like that, so it's going to stay on. And the other ones are all going to die off. So what we get is we get these 3 states are now on. These 3 cells are now on. So what happens to the next period? Well, let's just start, again, these ones to the left are all going to stay dead. But this one right here, because it's got one neighbor to the right on, is going to come to life. This one, because it has one neighbor to the right on, is going to come to life. But this one, which is in the center, has 3 in a row on, so it's going to die off. So we're going to get something that looks like that. So what we get is we get this sort of pattern spreading out. Well, again, we're doing this by hand. Let's try this in a more serious way using NetLogo. Okay, so we're going to set this up where there's one cell that's alive in the center, and then we're going to let it go, and we see that we get those 3, right? And now what we see is this really interesting pattern evolving as I move down. And notice how this is creating, now we see these different structures, right? We see smaller triangles, bigger triangles, and so on, right? And one of the things that's been proven about this rule, which is sort of interesting, is if I drew a line right down the center, like if I picked a particular cell and drew a line right down the center of its path over time, it's going to be a random sequence of ons and offs. So you wouldn't be able to tell, you wouldn't be able to predict what's going to happen the next period if you knew what happened the period before. So what this is an example. Rule 30 is an example of a rule that produces perfect randomness. All right. Here's the next rule, and this is rule 110. So remember, we get the rule: the 2's on, the 4's on, the 8's on, the 32's on, the 64's on. So we add those all up, we get 110. So let's think about this one again. We've got these 3 cells over here to the left, and these 3 cells over here to the right all have no neighbors on, so they're all going to stay off. Now this one has a neighbor to the right on, and so it's going to come on. This one right here, right, is currently on and with no neighbors on, so it's going to stay on. And this cell right here has a neighbor to the left on, right, but notice how it's going to then stay off, unlike in the previous case. Well, now if I go along, this one is going to stay off, this one's going to stay off, but this one, because it's got a neighbor to the right that's on, is in this configuration, so it's going to come to life. This one has two neighbors, and it has its on and its neighbor to the right on, so it's in this configuration, so it's going to stay on, right? But this cell right here, the original cell that was on, is in this configuration. It's on and the one that's right on, so it's going to stay on as well. And then finally, this cell right here is in the configuration it was in before, where its neighbor to the left is on, so it stays off. And so now we get something that looks like this, where we sort of get this increasing triangle. Now we could ask what happens to rule 110 as we let it run, and what we get is this is a map from Wolfram, we get this really interesting pattern, and this is going to be sort of complex. We see these particles that sort of move through space, and this rule 110 is classified as class 4 by Wolfram as a complex rule. All right? So what we've got, here's a better picture if I start with a random configuration. Here's rule 110. And again, we see all these sort of interesting particles moving through space. We see lines moving through. We see things like this interacting and then causing bigger things. So we see all sorts of really crunchy, interesting stuff. This is complex, right? It's very hard to make sense of. So what we've seen then, which is interesting, with this simple one-dimensional cellular automata model is it's easy to make rules where everything just dies. It's easy to make rules where everything just blinks. There's some rules where things appear to be random, and you can actually prove that they're random, like Rule 30. And then there's rules that, like Rule 110, right, that create this complexity. So what we can do then is we can ask, okay, here's the interesting question, why? Right? Why do some rules go to steady state, some rules blink, some rules random, and some rules complex? Before we get to that question of why, what creates complexity, what creates chaos, what creates order, let's just stop for a second and think about how profound these results are. 'Cause these are really simple models, much simpler than the game of life, and they can give us anything. And this has led some physicists and mathematicians to suggest that this may be how the world works in some sense, that everything may come from very simple rules. So all the complex things we see out there in the real world come from very simple binary interactions. So this led to the phrase by the physicist John Wheeler, it from bit. Now let me quote Wheeler here because it's really sort of profound. He says, it from bit, otherwise every it, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely, even if in some context indirectly, from the apparatus elicited answers to yes or no questions, binary choices, bits. It from bit symbolizes the idea that every item of the physical world has at its bottom, a very deep bottom in most instances, an immaterial source and explanation that which we call reality arises in the last analysis from the posing of yes-no questions and the registering of equipment-evoked responses. In short, that all things physical are information theoretic in origin and that this is a participatory universe. Okay, that's Wheeler in 1990. Okay, so Wheeler's basically saying this it from bit idea is that you can actually explain anything, right, by just simple yes-no questions at the core. And so the very, very deep bottom of reality could just be binary switches. So it, us, the universe, everything, could literally come from bit. Now that's a bit of a, that's a big leap from the simple one-dimensional cellular automata model. But again, the cellular automata model is capable of producing pretty much anything. So it's interesting. All right, so let's get to this question of how does it produce anything? What's going on? Well, Chris Langton, who is a researcher at the Santa Fe Institute, who got his PhD at Michigan studying these cellular automatas, came up with something he called Langton's lambda. And what lambda does is it tells us sort of what the outcomes look like. So let me explain what I mean. So remember that Wolfram numbered these rules from 1 to 256. Langton takes a much simpler approach. He just says, look, how many things go on? In this case, there's 3. So you can think of Langton's lambda as 3 or as 3/8. Either way, but it's just the percentage or the number of switches that are on. Right? So this rule would have a alpha, or lambda, of 0, or 0 over 8. And this one would have a rule of 1 over 8. So the Langton's lambda tells us the percentage of bits that are on. And this one, remember this was rule 30, right, would have a lambda of 4 over 8. Well, let's go back and look at these again. This one that has a lambda of 0 over 8, what's going to happen? Nothing, right? Everything's just going to die. Nothing interesting is going to happen. What's going to happen to this one that has a 1 over 8? Well, initially, a lot of stuff is going to die off, but then once everything dies off, everything's going to go on, but then once everything's on, it's all going to die off. So this thing's going to blink, right? What about rule 30, which has the lambda of 4 or 4 over 8? Well, remember this thing was chaotic, right? This was completely random. And what about rule 110, right? This was rule 110. This has a lambda of 5 over 8, and this thing was complex. Now, what you could think of then, you think, well, wait, the bigger lambda gets, the more likely we are to get something interesting. Well, that's not quite true, because think about when lambda is 8, right? When lambda is 8, then everything automatically goes on. So that's not going to be interesting either. So what's going to be interesting, it would seem to be, is sort of this in-between region, right? This region where you've got sort of either 2, 3, 4, 5, 6 things go on. Well, let's look at it. So here's all the rules in the one-dimensional cellular automata with 2 neighbors. Remember, if I sum this up, I'd get 256. If I want to know how many class 3 members this sort of chaos or random, and in that class there's 32 of them, right? And if we look, 20 of them have a lambda equal to 4. And they're all in this region between 2 and 6. Class 4 is the complex rules, right? In the complex rules, there's only 6 of them, and those all happen between 3 and 5, lambda between 3 and 5. So here's what's really interesting. Now we want to ask, what causes chaos and complexity? Well, it's this region right here. It's intermediate levels of interdependence, right? So a rule like this, which has a lambda of 7/8 or 7, right? Nothing interesting is going to happen. It's just pretty much going to go to everything being on, and then once everything's on, right, it's going to stay on. So it's going to be stable. So it's these intermediate levels where we see the complexity. So if you look at something like, this is the Nikkei index, where you see these incredibly complex patterns, what you'd expect is that these rules have substantial interdependence, right? Because that middle level means that whether I'm on or off depends a lot on what other people are doing. So if there's a lot of interdependence in the rules, you're going to see complex patterns like these things, right? Well, what happens in a market? Well, people's rules depend a lot on what other people are doing. So there's a lot of interdependence, and therefore you get these complex patterns. If there weren't interdependence, right, then you'd always go on or always go off, and nothing interesting would be happening. So what do we learn from this very, very simple toy model? First, we learn again that simple rules can combine to form just about anything. Incredibly simple rules. Second, we get this sort of profound idea of it from bit. And third, we get the complexity and randomness require some intermediate level of interdependency, right? So you can't have it be that like I always go on or always go off. You need interdependency in the actions in order to create complex phenomena. Okay, so that's one-dimensional cellular automata models. It's a toy model, but it gives us a deep insight. And that deep insight is if we see complexity out there in the world, it's likely because people's behaviors or the rules that things are following are interdependent. All right, thank you.